Very much, CL. Thank you for the invitation. It's really great to be back virtually. As you see that we also have an IES in Tsinghua and also a astronomy department. Although we are much younger and our sizes are much smaller, we are probably the place that best resembles Princeton. Okay, so today I'm going to talk about planet formation in general and from the perspective of magnetic fields. And this is work I've been doing with current and former members of my group, as well as my collaborators at MIT. Planet formation is a continuation of the star formation process in molecular clouds. And following the gravitational collapse of protostellar cores, you form a disk due to angular momentum conservation. While of course the real story is more complex, and there's due to magnetic fields, there's magnetic braking, etc. And we don't fully understand that process. But what we know is that at very early stages, the disks are embedded in the infalling envelope, and at a later stage, they become more transparent, and we call this protoplanetary disks. Their typical lifetime is a few million years. Their sizes ranges from about 10 to 100 AU. Typical mass is about 1% of stellar mass with large scatter, and they are also accreting at a typical rate of about 10 to minus 8 solar masses per year. And this is the stage we're going to focus on, and we anticipate planet formation. If planets do form in these disks, the formation process, the planets will be mostly assembled by the end of the disk lifetime. And a major revolution about these disks is really driven by ALMA, the large millimeter, sub-millimeter interferometer in Chile, which has really exquisite sensitivity and resolution. And thanks to ALMA, the originally innocent-looking smooth disks suddenly show copious substructures. And as more disks are surveyed, it becomes obvious that the substructures are ubiquitous, and they're dominated by ring-like substructures, and a small fraction of them also have some asymmetries, like spirals in this disk, and also some of them have some crescents, or maybe due to some vortices. And because planets can naturally produce many of the substructures, and the community are inclined now to call them, instead of protoplanetary disks, they call them planet forming disks, because we are essentially witness planet formation in action. So besides the excitements about extrasolar young stellar systems, our solar system have long been speculated to originate from the so-called solar nebula. Although we are nearly 5 billion years old, the conditions experienced in the solar nebula may be preserved in the remnants, mainly in the form of asteroids and comets. And when they fall onto the Earth, we have the opportunity to study them in great detail through the meteorites. And here is an example of the meteorite, of a carbonaceous meteorite. And you see this, there are many of these round, sub-millimeter sized objects. They are called congruents. And well, astronomers say the basic building blocks, so the dust grains and pebbles are the building blocks of planets. Planetary scientists studying meteorites, they would say congruents are the building blocks of planets. And from the textures, we know that these congruents have experienced some flash heating within minutes to over 1,000 Kelvin, followed by rapid cooling over a timescale of hours. How exactly that happened is still a mystery, and there are many competing theories. And also we see here this white irregular shaped stuff is the so-called calcium aluminum rich inclusions, or CAIs. They are formed in even higher temperature and with wide range of morphology and composition. But the most important fact is that they are the oldest materials we can date, and they essentially set the age 0 for the solar system. And in that regard, congruents are typically formed 1 to 3 million years after CAI. And similar to protoplanetary disks, and this field has also underwent a major breakthrough over the past decade. So the aforementioned congruents, their parent bodies are called congruents. And roughly speaking, they can be divided into two groups. the non-carbonaceous chondrites, and they are more similar to the Earth. They are dry, and they are likely to form in the inner asteroid belt. And the carbonaceous chondrites, they are more volatile rich, and so they are thought to be formed in the outer asteroid belt. And surprisingly, these two groups show very distinct compositions in nucleosynthetic isotopes. And here, this epsilon means the deviation from Earth composition in units of 0.1%. And you can clearly see that the non-carbonaceous chondrites, they cluster in this region, okay, and the carbonaceous chondrites, they cluster in that region. And this dichotomy is generally interpreted as there is something in the solar nebula that prevented the materials to mix from each other. And that something is usually attributed to the Jupiter, the formation of Jupiter, which then separates the materials between the inner and outer solar systems. And that's quite analogous to the substructures in protoplanetary disks, where what you see are the dust rings separated by gaps in between. So in this context, why do we care about magnetic fields? In order to understand planet formation, we know that almost all stages of planet formation, they are sensitive to the structure of the disks and how disks evolve, as well as the level of turbulence in the disks. And these are generally the consequences to mechanisms that govern angular momentum transport, okay, that really drive accretion and disk evolution. And we know that magnetic fields almost surely play a crucial role in this process. So to some extent, the major uncertainties in our understanding of planet formation theory is partly because we don't really understand disk magnetism. All right, so here is the plan of the talk. So I'm going to start by outlining the basic physics needed to understand the rest of this talk, and then I will separately talk about magnetism in the outer disk, which is most accessible to astronomical observations, and followed by magnetism in the inner disk. That's roughly within 10 AU or beyond 10 AU. So this is within 10 AU that is most accessible from meteorite records. Okay, so as mentioned earlier, the key question here is what drives angular momentum transport, and there are two ways to do it. And if there is some viscosity in the disk, we know viscosity, what they try to do is to erase any gradients in the system. And because the disk has differential rotation, right, the inner disk rotates faster than the outer disk. So viscosity, it will try to exert a stress that slows down the inner disk. And this process will make the inner disk lose angular momentum, right? And they will try to, then it will fall, spiral in, it will accrete. Whereas for the outer region, again, the stress will try to accelerate the rotation in the outer system, outer disk, and they will gain angular momentum and try to spread out. So you see that this will lead to an outward transport of angular momentum. And of course, in reality, the molecular microscopic viscosity in the gas is really negligible. And so you need some effective viscosity to serve for this mixing process. And that's usually attributed to turbulence, and either through the MRI or magnetorotational instability. And this is a powerful instability that is responsible for driving accretion in most astrophysical accretion disks. But there can also be pure instabilities of pure hydrodynamic origin that they can also drive turbulence. And in addition, even the disk is laminar, there's some laminar Maxwell stress that can serve the purpose as well. And alternatively, when we have a vertical magnetic field threading the disk, the system can launch a magnetized disk wind. And it do so by the following. So again, because the disk has differential rotation, right? It would, when you have vertical fields threading the disk, it tries to wind up the disk. But the magnetic fields, they behave like strings. They have tension, so they don't want to be. They tend to straighten. They don't want to be wound up. So when you wind up the field, they try to resist, and this will exert a torque to the disk which essentially extracts disk angular momentum and try to drive the accretion. And in the meantime, as you wind up the magnetic field, you build up magnetic pressure that tries to push the gas away. So this wind essentially carries away this angular momentum. And there's a long debate over which mechanism wins. And I would say the answer would really depend on disk physics. Okay, so then for protoplanetary disks, what are the governing disk physics? I would say it's mostly related to the fact that the disks are very poorly ionized. And because the disk is cold, and only the innermost region that is hot enough, there is some thermal ionization of alkali species. For the bulk of the disk, you have to rely on external sources of ionization, such as cosmic rays, stellar X-rays, and UV for the ionization. But they can only, but the typical ionization level from these processes is typically well below 10 to the minus 8. So it's extremely poorly ionized. So why do we care about ionization? Because that they determine the coupling between gas and magnetic field, right? Only charged particles can couple to magnetic fields. And when the disk is very poorly ionized, that will introduce so-called non-ideal MHD effect. So this is the only equation I'm going to show here. So, so this is the induction equation that governs how magnetic fields evolve. This is a normal inductive term, meaning magnetic fields frozen into the fluid. But when the disk is poorly ionized, you have three more terms called non-ideal MHD terms called ohmic resistivity, the Hall effect, and ambipolar diffusion. And these diffusion coefficients are all inversely proportional to the ionization fraction. So the more poorly ionized, the more important they are. And in addition, you can see the Hall term is proportional to B over rho, and ambipolar diffusion term is proportional to B square over rho square. So that gives you the relative scaling, okay, between among the three terms. Essentially, ambipolar diffusion will dominate in the low density regions with strong magnetic field, and ohmic will dominate in the densest region of the disk. And when you apply this to protoplanetary disk, you will realize that because ohmic is important for the density part, that's the midplane region of the inner disk. Okay, that's where ohmic dominates. And as you move up, as density drops, then you are dominated by the Hall effect. And as you further move up, the density drops further, you are dominated by ambipolar diffusion. And eventually in the very upper layer, thanks to especially far UV ionization, the ionization fraction is substantially boosted so that you are back to the so-called to the ideal MHD regime. And as you move radially outwards, again, as density drops, then you are dominated by the Hall effect in the midplane and followed by ambipolar diffusion. And then if you move radially further out, you are entirely dominated by ambipolar diffusion. So that's the dominant non-ideal MHD effects in the system. And another thing to notice is that when you have the Hall effect, okay, the outcome would depend on the polarity of the magnetic field. What do I mean by polarity? So you have the direction of rotation, and now by polarity I mean whether this large-scale field is aligned or anti-aligned with the rotation axis. And to see this, we ask what happens when we flip the magnetic field. And in this equation, if you flip the field, you see that all terms changes sign once, changes sign except for the Hall term, which changes sign twice, so it gives you this plus. And so that really means when you have the Hall terms, the outcome of the system would depend on the polarity. So you have to make two simulations, for instance, to study the effect of the Hall term. All right, so here's a very brief summary of the current understandings. And based on a series of works from myself and many other authors, we have more or less converged that in the inner region, the MRI is largely suppressed because it's suppressed by resistivity in the midplane and by ambipolar diffusion in the disk surface. And to drive accretion, you need MHD, magnetized disk wind. And this wind will also give you very significant mass loss. And again, due to the Hall term, the overall dynamics is polarity dependent. For the outer disk, I would say it's somewhat less well studied, and there are simulations of these winds, but we also expect that the MRI can operate despite they are being partially damped by ambipolar diffusion. So there are some ambiguities there. Okay. Okay, so now let me move to talk about magnetized gas dynamics, starting from the outer disk, that's a region roughly speaking beyond 1 AU. In this region, we know that the dominant effect is mainly ambipolar diffusion. At early times, we study this in so-called local shear and box simulation. You just take a local patch and make it Cartesian with shearing periodic boundary conditions. And this is very neat that you can study the local physics. So I did this with Jim, and we implement ambipolar diffusion. We study the behavior of the MRI as a function of how strong ambipolar diffusion is. And this is the time evolution of the Maxwell stress, which characterizes the strength of turbulence. And you can see as with more and more, the stronger ambipolar diffusion, the level of turbulence just decreases and eventually it's gets suppressed. So for more realistic level of ambipolar diffusion, you expect you're more or less at this black line. So there's a lot of reduction, but not completely suppressed. So this is very early simulations. But after a couple of years, when I looked back into the simulation more carefully, I found something quite unusual. Okay, and so this is a space-time plot. Okay, and the horizontal axis is time, vertical axis represents radial coordinates, and the top panel is the time evolution of the radial density profile. And you can see at a later time, you start to develop into this radial density variations at about 10% level. Okay, and well, this is not new and has been known for a few years from shear box simulations. But what's more striking is the bottom panel, which shows again the time evolution of the profile of the mean vertical field. You can see similar kind of variations, and in particular in regions with strong vertical field, the density of the gas gets depleted. Okay, in this region. And so essentially this local flux concentration tends to deplete the region, and that makes sense because you have stronger stress, so that in order to balance, it will give you a lower density in steady state. And so this is based on unstratified simulation. There's no vertical structure, just like the movie I just showed. We also find this in stratified simulation. Now you do have the vertical structure, and the effect is even stronger, right? You drive much stronger density variation, and that's strongly anti-correlated with the concentration of magnetic flux. But of course, this is local simulations. You can always argue that there are some caveats, but later people also find this flux concentration in global simulation. Although the existing simulations are mostly in 2D, and the resolutions are not good enough, and even in a handful of 3D simulations, the resolution were quite poor, and is far from sufficient to resolve the MRI. So the results remain somewhat questionable. Okay, so this is a project that I have long wanted to do until I have a Cine++ with the full capability of mesh refinement. So thank you, Jim. And until I find a really capable student, this is a former student, Cui. She's now a postdoc at Cambridge. So this Cine++ will allow us to do the most cost-effective simulations with a computational domain that opens all the way up to the polar region. And in the meantime, we can have mesh refinement to allow us to achieve a resolution comparable to the local simulation that we performed many years ago. And so here are the main parameters we have is how strong ambipolar diffusion is. It's characterized by this Alsace number AM. Typically, we anticipate AM should be on the order of 1-ish. So that's also the critical value. If AM is much larger than 1, it's more or less ideal MHD. It's much smaller than 1, you have very strong ambipolar diffusion. And so we can explore a wide range of AM. And also the level of disk magnetization that's characterized by the initial, the plasma beta of the initial vertical field. So typically, we expect the beta to be on the range of 10 to 1000 to 10 to the 5. And so we explore a wide range of beta as well. And so this is a fiducial simulation. We have 3 panels. This is the radial velocity to indicate the wind. And this is B theta, which indicates essentially theta at midplane is more or less vertical component of the magnetic field. And the third panel is B phi. So we have wind is launched from the beginning, and then you form you can see the wind is launched, and you form a current sheet, and in the midplane, and this is also where the accretion flow is. Right? The accretion flow always exists when you have B phi changes sign in this case. And later, the MRI is developed, and you can see the disk becomes quite turbulent, and the flow becomes stochastic. We run this for a very long time, 3,000 orbits at innermost region, and corresponding to 100 orbits at radius 10. From the simulations, we find that, yeah, you launch magnetized wind, and wind does dominate angular momentum transport. But the MRI disk is also very turbulent. The MRI also contributes significantly. In the meantime, you see that if you look at this BZ, okay, you can already see that vertical field is concentrated in these flux sheets, and they are dynamically evolving. If I play this again, right? They are dynamically evolving. Okay, and so we run many simulations, scan the parameters, and we can. This is a space-time plot of this essentially the radial profile of magnetic flux. Okay, and you can see in almost all cases you have strong magnetic flux concentration. Okay, except for this AM equals 10, that's close to ideal MHD, where the flux concentration is less effective. And also the process is stochastic. We can see that the magnetic flux, sometimes they can split, they can merge, and they can migrate in some cases. So this process is totally stochastic. So, so what's the consequence to substructure formation? So here is a sequence of surface density profiles from our fiducial run, and you can clearly see that it starts to develop into this substructure density bumps. And the location of the density bump, if you look at the final time, they exactly corresponds to the region where you get strong magnetic flux concentration, shown in the bottom panel in this black curve. And we also have this, this animation shows the, again, the evolution of the surface density profile for all our simulations. And you can see in all cases, probably except for this AM equals 10, where I say it's very MRI turbulent. So in almost all cases, you develop this kind of radial substructures. And their typical separation between these ring-like substructures is about 3 to 5 disk scale height, 3 to 5 H. And they are all dynamically evolving. And also because they are dynamically evolving, you never form very deep gaps. And so the surface density variation is generally modest, about 15 to 50%. Okay, so how does this compare with observations, right? So if ring-like separation is only 3 to 5 scale heights, given if HOR is 0.1, then you would expect to see 2 to 3 rings per log radius, and that's a lot. And observationally, you may not recall that we see something like that.
May I ask you a quick question, just for clarification? Sure. Aren't the simulations all 2D?
All 3D, sorry. These are all 3D simulations, but only show the azimuthally averaged. Yeah, so they fully resolve the MRI, yeah.
But do you have structure in the three-dimensional direction, so to speak, out of the plane?
We checked. There is not very prominent substructures in the phi direction.
Okay. And what is the skin depth? What is the skin depth? In terms
these are MHD simulations.
Oh, so there's no Hall effect at all.
There's no Hall effect, and if you were to, yeah, this we focus on the outer disk, right? So, and there the Hall effect is less important.
Understood. Thank you.
Okay, thanks for the question, for clarification. Okay,
right. So what the beta is in the regions where the magnetic flux is concentrated? It wasn't clear to me.
Okay, so right. Let me go to. So the vertical beta is 10 to the 4. Okay, and the level of concentration is I would say not that much. It's relative to the initial vertical field. Okay, so you can see in the region where flux get concentrated is about a factor of a few. Okay, compared to the initial. And of course, the dominant field is always the toroidal field. Toroidal B phi is usually a factor of 10-ish stronger than BZ. And B phi actually doesn't show the strong variations across rings or gaps, right? So if you just talk about the strength of B phi, other than changing sign, the strength of B phi is generally still smooth, right?
Thank you.
Okay. Okay. Okay, so to compare with observation, right? So these are the ALMA images you have from the D-sharp program I showed earlier. But very recently, very interestingly, this recent work by Jennings et al. Show that if you assume the disks are axisymmetric, okay, you can achieve a super resolution image, and which is essentially a super resolution. And with this super resolution technique, it showed that the disk actually likely possess a lot richer set of substructures, a lot more rings. And so maybe the disk even have even more substructures than we currently know. And I would say, I will not claim that all substructures are formed by this mechanism. And in fact, I do believe that this disk should have some hidden planets. But on the other hand, it's just natural to produce such closely packed and shallow substructures based on our study. Okay, now let me move a bit further to discuss the outer edges of the disk. Okay, so why do we consider the outer edge of the disk? As I mentioned, there are two ways to transport angular momentum. With turbulence, you can transport angular momentum really outward. In this case, you expect the disk to expand, right? You have this this well-known so-called viscous spreading. The disk should expand. And in the wind scenario, the general anticipation is that because the wind extracts angular momentum from the disk and carry it away, so the disk should shrink, right? So, and this distinction has been considered as the fundamental way to test which is the dominant mechanism that drives disk evolution, right? And in fact, there is some evidence that the disk does expand over time. Of course, this is statistical sense. People find that young systems tend to have smaller size compared to older systems, okay? And so this might be evidence against wind-driven accretion. With my postdoc Haifeng Yang, we looked into this problem. So we noticed that almost, is there a question?
Yeah, just to understand the previous plot. So is there a good reason to assume that the feeding of angular momentum is independent of time? So you have sort of a fixed circularization radius at different times? Which I think that's sort of implicit in the way you're interpreting the plot.
Right, right. So the implicit assumption here is that the disk is isolated at later phases. But I think more recent observations seem to suggest that there's also something called late infall. And even in later phases, there's this disk, some of the disks are still connected to some feeding from even larger scales in terms of in the form of streamers. So I would say this assumption of that the disks are isolated are not totally true. But nevertheless, people are still trying to test this idea of whether the disk overall expands or shrink over time. And in fact, there's a ALMA large program approved recently to test this. Yeah.
Thanks.
Okay. Okay, so with Haifeng, we are trying to, so we noticed that almost all MHD wind simulations, they are infinitely extended in radius, okay, and they're seeking for self-similar type solutions. But we ask, well, in more realistic truncated disks, right, what would happen, right? So here we set up this truncated disk, and with our truncation at about 30, and the density then tapers off. And then we initialize with open field lines, and then see what happens, right? Because of this outer truncation, you can see there will be a lack of pressure support beyond the truncation radius. So after you launch the wind, the magnetic field suddenly collapse and reconnect and form this closed loops. Okay, and then this situation will just continue. So over time, we can see this magnetic fields, this loops shrink and dissipate. So that's how magnetic flux get dissipated over time. And in the meantime, we also find there's significant mass loss through beyond the truncation radius. So that's somewhat similar to so-called external photoevaporation. Okay, so that's this is simulation, but the most interesting part, I would say, is that if you look at the flow structure.
There's another question.
Oh, okay.
Sorry, the evidence for disk expansion, is that based on line observations, the gas, or is it dust, which of course may migrate relative to the gas?
So this is mainly based on observations of CO. Okay, 12 CO. Okay.
Okay, thanks.
But there are also a lot of caveats related to chemistry, etc. And so, in fact, there's another study that, yeah, indicates there is some evidence, but not that strong evidence. Yeah.
Thanks.
Okay. Okay. All right. So I would say the most interesting part is that if we look at the flow structure from the simulations, you see that essentially separating from this point, inside of this region, the flow is accreting. Beyond this region, the flow is actually decreasing. And right, so from our simulation, we obtain something actually similar to visibly driven accretion disk. There's accretion flow and there's also decretion flow beyond certain radius. And why this happens? So we may look at, so this more or less represents the structure of the magnetic field loop. And this point is in fact exactly where the loop center is. And so essentially we have accretion flow inside the loop center and the decretion flow beyond the loop center. And the reason is also quite natural because whether you accrete or decrete depends on, is determined by the torque, mainly exerted by magnetic fields. And because the torque, because the vertical field changes sign across the loop. And actually the torque has a product with the vertical field. And so the sign of the torque also changes sign, okay, across the loop center, so that you naturally get accretion flow inside and decretion flow outside of the loop center. But whether the disk will really expand or not, that question is actually more complex. That depends on whether the center moves or not. Another question? Okay, maybe then I'll continue. So whether the disk would really expand or not would depend on whether the loop center expand or shrink. So that's a more complex question, depending on the environment. But overall, I would say that what we want to say is that whether disk will expand is not as simple as one would naively expect. Okay. All right. So next, I'm going to talk about implications to planet formation. So since substructures are discovered, they are considered, okay, as either consequences of planet formation, as there have been many works demonstrating planets can produce all kinds of substructures. And we do see planets in this PD-70 system. And in a few other systems, we do have found their kinematic signatures. So they are natural consequences of planet-disk interaction. But on the other hand, another interpretation is that they are precursors to planet formation. And in fact, we also find substructures in disks at very young embedded stages in this, say, class 1 IRS 63 system. And in particular, so these substructures are speculated to trigger planet formation because typically you don't expect planet form so rapidly. So this substructure may be the trigger to planet formation, in particular planetesimal formation. And planetesimal formation is essentially the conversion of millimeter-sized dust to kilometer-sized planetesimals. And this is the most crucial stage to planet formation because once you form planetesimals, they are massive enough so that gravity will do the rest of the work, right? But how do you get from millimeter size to kilometer size is actually the most difficult step in planet formation. So to start with this question, okay, we may first look at the dust dynamics in this ring-like substructures. So basically, when you have a ring-like substructures, what you have is a bump in surface density or pressure, right? Okay, and because now you have this positive pressure gradient here and negative pressure gradient there, and because of this additional force from pressure gradient, the gas would rotate at supercapillary speed here and subcapillary there, okay, on the other side. On the other hand, for dust particles, they still try to rotate at capillary speed so that they will feel a tailwind in the inner side and they will feel a headwind in the outer side, right? And with a tailwind, it will gain angular momentum So it will try to drift outwards. And here with a headwind, it loses angular momentum and will drift inwards. So essentially, dust will drift towards pressure maxima. And so what we observe in these ultramarines is essentially dust trapping, okay, into pressure maxima. And nevertheless, disk is also somewhat turbulent. So this concentration will not continue indefinitely, and turbulent diffusion will eventually determine the width of this ring. Okay, and by modeling the dust ring width, one can constrain the level of turbulence, which is given by this alpha over tau s. So tau s is the stopping time of the dust, and is proportional to dust size, and it's typically around 0.1 or so for millimeter size dust grain in outer disk. And so alpha, therefore, is roughly 10 to minus 3 to minus 2 in this estimate. So turbulence is modestly strong, right? So it's consistent with our MRI simulation results. Then what does it mean for planetesimal formation? So in a smooth disk, right, the most widely adopted theory for planetesimal formation is the streaming instability. And basically, in smooth disk, because the dust has its radial drift towards pressure, the higher pressure, right? They always drift inwards in a smooth disk. Goodman and Pindor, and also Udi and Goodman, showed that if you incorporate the back reaction from dust to gas, and that will lead to an instability called streaming instability. And this streaming instability has a magic that they can concentrate dust particles into very high density clumps, and so that their self-gravity of the clump can just directly drive the collapse and form planetesimals directly. Okay, and so this has attracted a lot of attention and has continued to be a hot topic. And I studied this as a graduate student, following the pioneering work of Anders Johansson. However, recently, the community started to realize a big problem about streaming instability, which is, well, streaming instability generates its own turbulence, but there's external turbulence, okay, pre-existing external turbulence. They tend to suppress the streaming instability, and they no longer form planetesimals. Okay, so if the outer disk is turbulent, then this is a problem. With former student Ziyan Xu, she just started her postdoc at Lyon. We use Athena, the hybrid gas particle code, to simulate dust dynamics in the presence of the MRI. And here, this animation, maybe it's not playing, but anyway, you can see that in the simulation, the gas is fully turbulent and dust settled to the midplane, and with turbulent diffusion, determine the vertical thickness of the dust layer. And you can also see that the distribution of the dust is not very uniform. And in fact, recall that we mentioned dust, the MRI itself can produce density variations. So what we see here is actually some dust trapping in pressure bumps created from the MRI. And now let's look at dust clumping from the simulations. So this plot shows the time evolution of the maximum particle density as a function of time. And the different lines correspond to different solid abundance, okay, which is essentially dust to gas mass ratio. So 0.01 is sort of canonical value. And we can essentially, and we also show this, the dashed line is the Roche density, okay? So if this dust density exceeds Roche density, we can say that it's dense enough to have gravitational collapse to form planetesimals. And you can see feedback is crucial. And if we don't have feedback, we have the black line, right? So if you turn on feedback, you can still form planetesimals. And compared with pure hydrodynamic run without the MRI, you can see that with hydrodynamics, you need to solid abundance reaching 0.04 to form planetesimals. But with MRI, it's actually easier rather than being more difficult. So that's what we find. And to understand why, and we looked at the space-time evolution of the gas density, okay? And clearly you can see this is structure traces the density bump, right? Formed from the MRI. And we find that actually there are times where this bump is strong, okay? Strong enough to overcome the background pressure gradient. So you form you really form a pressure maxima here. And there are also the time where the bump is not so strong, which is not enough to overcome background pressure gradient. And we find that dust clumping occurs only when this bump is strong enough to overcome background pressure gradient. So only clumping only occurs at a real pressure maximum. So the condition we find for dust clumping in turbulent disk is that you need dust back reaction similar to streaming instability, and you need a pressure maxima, okay? And so that's a simulation where we don't fully control the bump, but to further verify this result, we have more controlled experiment where we force the bump, okay? By doing some forcing so that we form a gas pressure bump in the simulation, and we see what happens to the dust. And we see that again, when you turn on feedback, and you easily reach very high, trigger the clumping. And so dust clumping happens whenever feedback is turned on. Is there other questions? No. Okay. All right. So next, let me talk about another category that is planet-disk interaction. So this has been extensively studied, and we know planets can form all sorts of disk substructures. So here we focus on massive planets, and massive enough to clear out its orbital region to open a gap. Of course, there are many questions behind this problem, such as how deep a planet can open a gap, and the rate of planet migration from this interaction, and also the circumplanetary disk. We anticipate massive planets can have its own disks as well. And in terms of observational signatures, one salient signature is so-called meridional flow, where in pure hydro simulations, people find that near the planet, you have the gas falling from high altitude, okay, down to the planet. And this is actually observed. However, all the existing studies of planet-disk interaction are almost exclusively done with pure hydrodynamics with or without viscosity. Okay, but if wind is playing a dominant role in driving angular momentum transport, many questions that I just mentioned will likely to have different answers. So with my postdoc, Yuhiko Aoyama, we've been again using Tsinghua to study planet-disk interaction in such MHD windy disks. And this is probably the first simulation of this kind. And our disk is weakly MRI turbulent with ambiguous diffusion, and also we have vertical field to launch the disk wind. And this animation shows the evolution of the gas density, and you can clearly see that it opens a gap. And also there are some weak vortices actually outside of the gap region. And this slide shows the phi velocity, and clearly you see it launches a wind, and the velocity becomes super Keplerian. And here is a toroidal magnetic field which dominates the wind region. And we can look further into the simulation, and this is the space-time plot. And essentially, this you can see that how this gap gets gradually opened by the planet. But more interestingly, if you look at the second, the right figure, you can see magnetic flux just get concentrated to the gap. So the planet opens the gap, and then magnetic flux just try to find where the gap is and then get concentrated. And you can also see from more directly from the right movie. And what's showing here is the magnetic flux, equidistance magnetic flux surfaces. And you can see that as the planet gradually open up, magnetic flux also gets concentrated into this gap region. And because of this, actually we found that the gap region, okay, so A is more strongly magnetized, and so that potentially if you form circumbinary disk, for instance, it's also going to be strongly magnetized. And B, because of flux concentration, this gap can get deeper and wider than the pure viscous case. And we have also seen signatures of meridional flows at low latitude, and you still have the wind at high latitude. So the phenomena are quite rich, and we're still sorting out. And before finishing this part, just want to mention that we are also developing a multifluid dust module for Tsinghua++, and this is the work done by my postdoc Pinghui Huang. And it's built upon Tsinghua++, and we can have arbitrary number of dust species with back reaction. We have wide range of integrators, including a fully implicit second order integrator. We also implemented consistent concentration diffusion with feedback. And this is just a test of the streaming instability. We chose this test such that the outcome depends on resolution. So we have mesh refinement. So the instability first show up in the finest grid, and then a coarser grid gradually catches up. And so we plan to use this to study planet-disk interaction and to compare and to test observational signatures and examine the role of dust feedback, etc. Okay, so finally, let me move to the inner disk region within about 10 AU. So I'm going to also transition from theory to observations. But so far we haven't really detected magnetic field from protoplanetary disk, and there are only some upper limits. But the observation that I'm going to talk about comes from the so-called paleomagnetic measurements. So what is paleomagnetism? So it is the inference of ancient magnetic field recorded by planetary materials. And basically, certain rocks can record the ambient magnetic field when they cool, they crystallize or accrete in the form of so-called natural remnant magnetization. And there are several subcategories. And the recorded magnetization is proportional to the ambient field when the rock was magnetized with some proportional coefficient chi, and you can essentially recover this chi from laboratory experiments. So it's a major subfield of geoscience, and one can do many things once you know the magnetization history of certain rocks. It was applied to meteorites since the late 1950s. But the nature and meaning of the meteorite magnetization process was only understood in great detail over the past decade. And you can check this review paper I wrote with my collaborator, Ben Wise, who is a leading expert in this field. And basically where we can use the meteorite paleomagnetism to constrain the magnetic field in the solar nebula. So the advantage of this is that, well, you can directly measure the field strength, which is not something you can do from astronomical observation, right? From Zeeman, you can only get the line of sight average field strength. You can have age information because you can date the meteorites. And you can also have measured, you can also measure instantaneous to time average field strength depending on how the magnetization was acquired. Some is more rapid, some takes a long time. So you can have different measured mean field in different scales. And there are also obvious disadvantages because, well, you don't know the field orientation. The location is unknown, right? We can only have educated guess where the meteorite parent body is coming from. We are also dealing with the small number statistics, but this is improving. Okay, so how do people do this? So first, you want to find a meteorite that is sufficiently pristine or unaltered by subsequent geological processes. And here is an example from the Semakona chondrite. It's among the most pristine ordinary chondrite. And the gray region here contain submicron-sized crystals called camosite that is made of nearly pure iron, okay, as seen in this transmission electrons microscopy images. And these are really the high fidelity magnetic field recorders, and they can record the ambient field when they cool down below their Curie temperature, which is 780 degrees Celsius. And because we know congruents have experienced this flash heating events followed by rapid cooling, so the expectation is that they can record the ambient field during congruent formation event. And there are a lot of works to do to retrieve and verify the paleomagnetic field, which is far from my expertise. And just want to show this test, and that's a test needed to convince yourself that you're not doing something crazy. So essentially, if the fields are recorded by congruents during congruent formation, at that time they are just free particles. And so after they get incorporated into their parent body, you would expect the orientation of the magnetic field from individual congruents to be random, right? And so people indeed do that test. And so this is a stereographic projection of the orientation from each of the congruents from the Semakona chondrite. And you can see by eye that they are consistent with being random, right? Okay, so now you're you can rest assured. Okay, so next thing is once you have the field strength, how do we interpret the results? And when the way
there's a question.
Okay.
Just to the density of a chondrule is obviously enormous compared to the density of the ambient disk. So is there any issue about magnetic field amplification during compression to form a chondrule, or is it decoupled during that process?
Yes, so that's one of the uncertainties because we don't quite understand the chondrule formation mechanism. And there are different theories, and there are nebula shocks. If this happens in nebula shock, there would be some compression. But I would say strong compression only occurs when you have those kind of grand design spiral, large scale spiral shocks that you may need to form, say, from gravitationally unstable disks. But that's one possibility. But I think but other scenarios like compact jetting from planetesimal collision, that's probably less of an issue because planetesimals, they don't really trigger very strong, They have some bow shocks, but not necessarily lead to very strong field compression. So that's so again, yeah, because we don't really understand chondrule formation mechanism, there are always uncertainties behind the interpretation. But currently, we are treating, we are assuming that it's largely recording the nebula field. Yeah. Okay. Okay. So under that assumption, then the question is, how do we interpret the result? Recall that so the way we do this is to do with angular momentum transport, right? Because magnetic field is driving angular momentum transport, there should be a relation between the field strength and accretion rate. And more quantitatively, if you take a local box and calculate the angular momentum flux across the faces of this box, right? There's angular momentum flux from the accretion flow, angular momentum flux from the radial transport of the angular momentum, and from the vertical transport of the angular momentum, where in this case, it's mainly record the B fields in the surface, and they should sum up to 0, right? And depending on which dominates, you can equate this term with this term, then you get the radial expectation from the radial transport, and equate these two, you can get the expectation from vertical transport. And here's the result, and which is a generalization of my semester project with Jeremy. So in the case of radial transport for typical 10⁻⁸ solar masses per year's accretion rate, you would expect field strength to be about 1 Gauss at 1 AU, okay? And with vertical transport, the expected field strength is about 10 times lower because wind is more efficient because it has a long lever arm over R compared to the viscous case, which is H. But there's also a geometric factor here because that equation, that formula, this conversion, we are essentially translating m dot to the surface magnetic field, right? But we are recording mid-plane field by the meteorites. So there is a geometric factor between B field strength at the midplane over field strength in the surface. And there are also geometric factors regarding B phi over BZ, right? And so how do we get this geometric corrections? We do this from simulations, and this is simulations I did a few years ago that incorporating all 3 non-ideal effects. And recall that we have the Hall effect, then the result depends on the polarity. And with aligned polarity, there is the so-called Hall shear instability, which strongly amplifies the midplane horizontal component, especially phi component of the magnetic field. And in this case, this M, the ratio of B midplane to B surface is about 10. And in the anti-aligned case, there's no such amplification, so the ratio is about 1. And after you plug in all these geometric factors, and here's the result from paleomagnetic measurements. You can see there are only a handful of data points, and they're mostly upper or lower limits, right? So we divide them into 2 groups for between those whose ages are 3 million years after CI formation, and those who are less than 3 million years. And for those less than 3 million years, there's only one from that Semicona chondrite, okay? And that's a non-carbonaceous chondrite, so we expect the their formation distance to be in the inner asteroid belt to be 2 to 3 AU. Of course, that's an educated guess. And for others, the CN, CR, CV, these are carbonaceous chondrites. So we anticipate, so we guess their formation distance to be about 3 to 7 AU. And so these three lines mark the anticipated field strengths based on accretion rate of 10 to minus 7, 10 to minus 8, 10 to minus 9 solar masses per year. A solid line corresponds to the case where background field is aligned with rotation. Dotted line corresponds to the anti-aligned case. And so basically we see the semicona chondrites, their results are consistent with standard accretion rate, 10 to minus 8, in the aligned field geometry, okay? And also for those older objects, you can see there are stringent upper limits, okay, from these angrites and from the CV chondrules. And their ages are about 4 million years. And so if we translate to accretion rate, you would say there's not much accretion going on at that time. So if you associate accretion with the presence of the nebula, that can place constraints to the nebula lifetime. And very recently, that was early this year, very recently, last month, Kue Borlina, a PhD student from Ben Weiss group, published another very solid measurement from the CO chondrules. So this is the second one with very solid field strength. The surprising thing is that despite of having at larger distance, the field strength is actually stronger. So in brief, what we have is that we have the field strength of 0.5 Gauss at 2 AU and 1 Gauss at 5 AU, okay? Because given that we anticipate given the accretion rate, right, the accretion rate should scale as b squared times r to the 5/2. That would mean a mismatch in accretion rate by a factor of 40. Okay, that's quite substantial. Well, of course, there are many caveats, and we don't know exactly where they form. We're dealing with small number statistics. There are many other uncertainties. Well, for now, let's put this aside and ask the question, if this is true, what would be the astrophysical implications? So the scenario we come up with is that we favor is that we know MHD winds are so-called magnetothermal in nature. They have very significant mass loss. And if you have with mass loss rate comparable to accretion rate, so this is a simulation of Li Wang. And so this is the cumulative mass loss rate over radius, and this is the accretion rate. So you can see total mass loss rate really exceeds accretion rate. So that means you can really not maintain a steady state with constant accretion rate. And you're probably more like this situation. You have higher accretion rate at larger radii and smaller accretion at smaller radii, so that the mass loss takes care of the rest. Well, this is in the right direction, but may not account for that factor of 40 mismatch. So maybe the presence of Jupiter is doing something, okay? And so we're still trying to see this. So this is pure speculation, but I would say more work on both sides are needed. Okay, so I think I'm out of time. So here are the summary. So I talked about the magnetism of the outer disk. We find that wind still dominates angular momentum transport with significant contribution from the MRI. We found spontaneous magnetic flux concentration that naturally leads to formation of disk substructures. And we found wind-driven disks can still have outer disk expansion that's similar to viscous spreading. For planet formation, we find that in turbulent disks, planetesimal formation can occur in pressure maxima, in region where you have real pressure maxima. And we find massive planets can open gaps that really attract magnetic flux that enhance gap opening, etc. With many other consequences. For magnetism in the inner disk, so the solar nebula paleomagnetism is consistent with wind-driven disk with aligned vertical field. But we also see some anomalies that may imply severe mass loss between the carbonaceous and non-carbonaceous reservoirs. Thank you. Okay.
Very much, Xuening. I have a question, Xuening. First, I wanted to say thank you for the 3 really beautiful colloquia. And so although I actually think it was 4. So my question is, could you give us some intuition into why the magnetic field concentrates in these lower density regions within the disk?
Right, so this is not something not very well understood. what's easier to understand is that if magnetic flux concentrate, it tends to deplete the local regions, right? Because you can drive wind that depletes the mass, but also you have angular momentum transport that also remove the mass from the local region. So that part is easier to understand. But what's not so easy to understand.
Also in the case without a wind, right? With
Yes. I think both. There's a mass loss and angular momentum removal. So I think both will try to deplete the local region. So that part is more straightforward. What's not so straightforward is why do magnetic flux concentrate at first place? And I would say there are sort of phenomenologically based theories. And I also have a sort of just some drawing to speculate the cause, but I would say there's no consensus yet.
Great, thank you.
So there are several questions answered. Who's the first? Jeremy?
Yes, there was an awful lot of material, as Eve just pointed out, in this, and provokes many, many questions. I'd love to ask you about flux migration, but instead, let me ask something about the magnetic, the paleomagnetic measurements. Several years ago, maybe it was 10 or more, Ben Weiss used to worry that maybe the magnetism was acquired by these objects sitting on parent bodies that were differentiated and had core dynamos. Were those different sorts of rocks, not chondrules? I mean, you made a point about the random direction of the field. Obviously, he's changed. He's no longer worrying about that, but what's the difference? In other words, it was not the nebular field, but a field created by dynamo in some sort of differentiated body whose core had become molten.
Right. So I think Ben works a lot on this meteorite magnetism, and he has many other works that study the dynamo process, the dynamo asteroid dynamos. And so I think it all depends on what kind of meteorites that you pick. And so for this chondrites, so this chondrites, mostly their parent bodies are undifferentiated. And so it's more likely to record a nebular field. But I think he also worked on other kinds of meteorites where they have a partially melted or fully differentiated parent body, and with those samples, he is studying parent body dynamos. So I think that's all depends on what sample you pick, what meteorites you pick.
And Bruce?
Thank you.
Beautiful talk, Xuening. Thank you very much. Could you just comment on the degree to which the conclusions about both the disk wind and the spreading of the disk depend upon the outer boundary conditions? And how much uncertainty there is about how to do the outer boundary conditions in a way that would be representative of what goes on in actual star-forming clouds?
Okay, so let me come back to this. So what we find is that, first of all, our box is sufficiently extended that that we don't need to worry the outer boundary too much. And also, when we start the simulation, we do have imagined there may be an envelope outside of this truncated disk. But what we find is that as we start to run the simulation, the initial envelope that we put in is blown away because the wind just blowing away everything. But on the other hand, we also tried if we make the envelope too massive, okay, they will collapse and they will push things in. So they will squeeze magnetic field into the disk, into the disk outer edges. Since we are here, we are mainly studying more of an idealized problem with isolated disks. So I would say this is appropriate. But in reality, for instance, recent observations indicate there are also streamers, and that will certainly complicate the story.
Thank you.
A second. Wendy?
Okay, it's my turn. So I want to ask about the grain dynamics. So,
Okay.
I wonder what kind of coupling did you include between the grain and gas, and also the grain motion, individual grains? Do you include not only the gas drag, but let's say Lorentz force? And
You're
other
talking
things?
about the planetesimal formations?
No, the grain concentration. So the grain density, you have to concentrate them above the Roche density such that they can grow. They can gravitationally grow. So I wonder about what kind of a grain dynamics in terms of individual grain particles, what kind of motion do you include? Or is you have a fluid-like grain grain which suffers global forces, not individual ones?
Okay, so these are dust particles. So we treat the grains in this simulation, they are treated as particles.
And they're big particles. They're big in terms of mass. Are they small ones?
Well, for this purpose, you know, technically we call them super particles. Each one represents a swamp of many particles with same properties. There's no collision, and the interaction with gas is purely by gas drag, aerodynamic drag. And there's no grain collision in this simulation.
Yeah, when I was at Caltech, so Phil Hopkins was advocating that when you include Lorentz force, I'm not sure what exactly forces they included. They seem to say they seem to suggest that there are other instabilities other than the streaming instabilities that can concentrate dust grain density, local density to like, I don't know, billions of more than the mean density somehow.
Yes, I believe those, what he had in mind was more on the larger scales, like dust concentration in molecular clouds that may affect star formation, etc. But and in those cases, because of the interstellar radiation field or other radiation fields, the dust are expected to have a very large carry systematic charge. But here, because the disk is very poorly ionized, the dust do carry some small amount of charge, but and there have been some studies that they may affect dust coagulation to some extent, but it's unlikely that they can strongly affect the dynamics, I would say. Yeah.
Oh, I see.
Yeah. Also, yeah, these are very big dust compared to interstellar dust. Yeah. We're talking about millimeter size. Yeah.
Yeah. Thanks.
Yeah. Hi, Xuening. Great talk. Just wanted to ask, you showed that plot where you kind of had like a loop and then there was an accretion and a decretion flow kind of on either side of it. Yeah. What determines where the center of that loop is? Is there some intuitive way of kind of figuring that out, or does it just come out of simulations?
Yeah, so far it just come out of the simulations, and but empirically we find that if we change the level of ionization, we can change whether this loop moves inward or moves outward over time. So that's something we don't fully understand, but just phenomenologically, that's what we see. And I would say that may have important consequences regarding whether the disk expands or the disk just get rid of some materials and then continue to shrink. I think that needs to be better understood.
Thanks.
I don't see other questions online. Any question here? Oh, yes.
So in your models where you show the development of the pressure maximum, I'm curious if you ever see the development of the Rossby wave instability, and does that have any consequences for trapping in the disk?
Okay, actually, in this simulation, we do see the triggering of the Rossby wave instability, and you can, after you wait for long enough, you can see the presence of actually a weak vortex, right, outside of this planet. But this simulation doesn't have particles or dust fluids, so we cannot say too much about the dust trapping. But so this is the simulation with relatively lower mass. It's just a thermal mass. We also have 5 thermal mass planets, and that will give you a stronger vortex. Okay, so I think that's also, these are all interesting questions that we hope to investigate in the future when we have the dust fluid model working.
Jeremy, is this a new question? I see our raised hand.
I see Jeremy, you have your hands raised.
If I can be allowed another question. Yeah, what do you make of the observational constraints on turbulence by looking at widths of and shapes of CO lines by Meredith Hughes and others? Is it something that we should, I mean, do you think that's a meaningful constraint on the presence of MRI turbulence or winds for that matter, the averages?
Right, so yeah, so there are some controversies in the community regarding those measurements, mainly the fact that those modeling, they are essentially fitting, they have a parameterized background disk model, okay? And you know, the constraints on turbulent broadening is extremely sensitive to your temperature prescription. Yeah, I think they have done the best they can, but I think there's still some doubts about whether that approach is good enough to constrain the turbulence. But I think there's one source, DM tau, I think it's pretty unambiguous that they find very strong evidence of very strong turbulence. That's a very recent work, but earlier observations tend to find low turbulence in a few other disks. Yeah.
Thanks.
Okay, so if there are no other questions, thank you very much, Xuening.
Thank you.
Oh, there's another question. Oh.